You know what I was doing the other night? Just standing outside. Just standing there, looking up at the sky. And it occurred to me, it really hit me, that the sky is dark. And I thought, well, of course it's dark. It's nighttime. Feynman, go back inside. But then I thought, wait a second, because here's the thing. The universe is full of stars. Absolutely stuffed with them. Billions of galaxies, each with hundreds of billions of stars. And in every direction you look, no matter which way you point, there should be a star out there somewhere along that line. So why isn't the whole sky just blazing? Why isn't every single patch of the night sky as bright as the surface of the sun? That's a real question. That is not a stupid question. In fact, a fellow named Olbers asked it back in the 1800s, and it bothered people for a very long time. It still sort of bothers me in a fun kind of way. Now let me give you an analogy, and I have to warn you it's not quite right, but it'll get us started. Imagine you're standing in a forest. A really, really big forest. Infinite forest, let's say. Trees in every direction, as far as you could go. Now, if you look in any direction, your line of sight is going to hit a tree trunk eventually, right? You won't be able to see through to open sky, because in an infinite forest there are no gaps. Every line of sight terminates on wood. The same logic should apply to stars. Every line of sight out into an infinite universe full of stars should eventually land on a star. And a star is bright. It is seriously, almost offensively bright. So the whole sky should be as bright as the surface of a star. Every single bit of it. But it isn't. And now you might say, well, maybe the stars are just too far away. Maybe the light fades with distance, and that's why distant stars don't matter much. And I thought that too for a moment. But here is the thing, and this is where it gets a little sneaky. Yes, a star that is twice as far away is 4 times dimmer. But at twice the distance, there is also a shell of space around us that is 4 times bigger, meaning roughly 4 times more stars. So the extra stars exactly compensate for the dimness. You can't escape it that way. The math doesn't let you. I remember once, years ago, I was talking with a colleague about this. We were just sitting around, and I floated that same idea. Maybe it just fades away. And he looked at me and said, no, the numbers cancel. And I sat there for a moment, and I thought about it, and I realized he was completely right, and I had a kind of sinking feeling, which is actually a wonderful feeling because it means you're about to learn something. So what is actually going on? Well, it turns out, and this is one of those things where once you really grasp it, you can't quite see the sky the same way again. It turns out the universe is not infinite in time. That is the key. The universe had a beginning. About 13.8 billion years ago, give or take, everything started. A hot, dense, extraordinarily energetic beginning that we call the Big Bang, which is actually a terrible name because it wasn't really a bang and it wasn't really big in the way we normally mean big. But never mind that, the name stuck. Now, light travels fast, fantastically fast, about 186,000 miles per second, which is so fast that it circles the Earth 7 times in a single second. But fast is not the same as infinite. And so in 13.8 billion years, light can only have traveled a certain distance. Beyond that distance, there's a kind of horizon. And the stars beyond that horizon, their light is still on its way. It left its source. It's been traveling faithfully toward us for billions of years. But it hasn't arrived yet. It simply hasn't had enough time. So the sky is dark, not because the universe is empty. The sky is dark because the universe is young. And I find that when I really sit with it, one of the most beautiful ideas I've ever encountered. The darkness itself is telling you something. It's telling you there was a beginning. Every dark patch between the stars is in a sense a window into the finite age of everything. Now let me push this one level further because the universe has another trick up its sleeve. And this one Edwin Hubble figured out back in the 1920s, and it was a genuinely shocking discovery, the kind of thing where you wonder how people went about their days normally after finding it out. The universe is expanding. Every galaxy is moving away from every other galaxy. And the farther away a galaxy is, the faster it's receding. Now this sounds like everything is running away from us, like we're somehow in the middle, and everything is fleeing, which would be a very peculiar situation. But it's not like that. It's not that the galaxies are moving through space. Space itself is stretching. Everywhere, all at once. The analogy I like, and it's not perfect, no analogy ever is if you take a rubber balloon and draw dots on it with a marker, and then blow it up, every dot moves away from every other dot, not because the dots are running, because the surface they're sitting on is expanding. Any dot you pick feels like the center because everything else is moving away from it. There is no center. The expansion is the thing itself. Now here is where it connects back to our dark sky. When a source of light is moving away from you, the light gets stretched. The wavelength gets longer. You've probably heard a car horn drop in pitch as it drives past you and moves away. That's the Doppler effect, and light does something similar. When the source is receding, the light shifts toward longer wavelengths, toward the red end of the spectrum. We call it redshift. And for very distant galaxies moving away from us very quickly, that light gets shifted so far, the wavelength gets so long, that it drops right out of the visible range entirely. It becomes infrared light, which your eyes can't see. Farther still, it becomes microwave radiation, radio waves, completely invisible to your naked eye. So even the light that does manage to cross the distance to reach us, a lot of it has been stretched into invisibility by the time it arrives. The universe is conspiring in two separate ways to give us a dark sky. One, it hasn't been around long enough. Two, it's been stretching and reddening the ancient light until it quietly disappears. Now, there's something else I have to tell you because it's too wonderful to leave out. All of that stretching and cooling, the microwave radiation that used to be visible light from the very early universe, it's still here. It fills the entire sky uniformly. Every direction you look, if you had microwave-sensitive eyes, you'd see this faint ancient glow coming from everywhere at once. We call it the cosmic microwave background, and it is literally the afterglow of the early universe. The light that has been traveling since about 380,000 years after the Big Bang, when things finally cooled enough for light to travel freely for the first time. It was there all along. And when two scientists named Penzias and Wilson accidentally detected it in 1965, they thought there was something wrong with their antenna. They even cleaned pigeon droppings off the equipment trying to get rid of the signal. And it turned out to be the oldest light in the observable universe sitting in their antenna, demanding to be noticed. I get a kick out of that. I genuinely get a kick out of that. Now, I want to be honest with you about something, because I think honesty is the most interesting part of any scientific conversation. There are questions here I cannot answer. Questions nobody can answer. Why did the universe begin at all? What was there before the Big Bang, if before even means anything in that context? Why did it start in the particular state it did? A hot, dense, low-entropy state that would eventually allow atoms to form, and then stars, and then heavier elements forged inside those stars, and then planets, and then whatever came after. I don't know. I mean, I really don't know. And I'm not saying that to be modest. I'm saying it because that is the true and accurate state of our knowledge. There are mathematical frameworks that are sophisticated and beautiful. There are ideas about what might have come before or whether the question even makes sense, and some of them are fascinating. But a framework is not the same as understanding. And I think it does people a disservice to pretend otherwise. What I find most exciting is not that we've solved it, it's that we've understood enough to know exactly where the mystery begins. We can draw the line right here, this is what we know, and past this line it gets genuinely strange. And that line keeps moving, which means we keep learning. And that is a very good situation to be in. So here you are. You step outside tonight. Maybe you're somewhere with dark skies, out in the country somewhere, away from city lights, and you actually see the stars properly, thousands of them. And between them, darkness, vast, cool darkness. And now you know what that darkness actually is. It isn't nothing. It's the edge of what light has had time to cross. It's the finite age of the universe written in black across the sky. It's the stretched and reddened ghosts of ancient light that your eyes can no longer detect. It's the expansion of space itself, quietly pulling the distant galaxies over a horizon you'll never reach. Every dark patch between the stars is the universe telling you something about its own history. About how long it's been here, about how it's changing, about what it was like before anything you'd recognize existed. And somewhere out beyond that horizon there are stars whose light is still traveling toward us right now, has been traveling for billions of years, will arrive eventually long after anyone is here to see it. All the rest of it is still on its way, and I'll leave that one for you to think about.